Welcome to this lecture series in group theory. In this lecture, we'll be looking at the notion of subgroups. And before we get into the material, let us recall a very simple and basic fact that we have discussed previously. So let G be a group, and it's a very, very basic fact, in fact. So let G be a group and X be some member of G. Then there's a unique element Y in G such that this equation holds. And this element is called the inverse of X. Right, so just make sure that we follow this and let's get started. So let us motivate the notion of a subgroup. So suppose we talk about the linear group GL2R. So what is GL2R supposed to be philosophically? It is supposed to be set of all the linear symmetries of R2. R2 is a vector space, so it has a linear structure, and we can ask for all those transformations of R2 which preserve this linear structure. So that is the name that we give to it, GL2R. And we saw that this is a group under composition of linear transformations. All right. But R2 is much more than just a vector space. It has, for instance, a notion of distance. So one can ask for those transformations of R2 which also preserve distance in addition to preserving the linear structure. And we saw that, or perhaps I did not say that very explicitly, but it is a fact that group of transformations which preserve the linear structure as well as distances is precisely the orthogonal group. We gave a very descriptive definition of the orthogonal group, perhaps, but that's what it is. So anyway, the point I'm trying to make is that one can look at more structure in the object that we are trying to form the group of symmetries of and exploit that to create smaller group of symmetries. So we had an original group of symmetries, which was just talking about linear symmetries, but we can talk about smaller group of symmetries. Like here, we have the orthogonal group. So that's the idea of a subgroup. A group is supposed to be the set of symmetries of some abstract object hidden from us. A subgroup of it is supposed to be a set of special symmetries which sort of preserves more things in the abstract object. Anyway, that doesn't make sense. It will ultimately make sense at some point. Right now, let's get into the formal definition. So let G be a group and H be a subset of it. We say that H is a subgroup of G if, first of all, H is closed under the binary operation of G, meaning what? Meaning that whenever you pick two elements in H, the binary operation of X and Y, the binary operation of X and Y is also in H, which we will also call that, we'll also refer to this fact by saying that H is closed under multiplication. So this multiplication has not to be confused with the multiplication of real numbers at all, but we will say it that way. All right, so okay, so we say that H is a subgroup if, first of all, it is closed under multiplication, and the restriction of the binary operation to H cross H makes H into a group. So first of all, this makes sense because of the first one. If you restrict star to H cross H, the image does land in H because of the first one. And I should technically write this because star is a map from G cross G to G. So when we restrict star to H cross H, we should make this notation, but this gets cumbersome and nobody does this, and I also won't do this. Okay, so this is the definition of a subgroup. It should be closed under multiplication, and the restriction of the binary operation to H cross H should make H into a group. All right, and notationally, we denote this by this symbol, H less than equal to G. This would mean that H is a subgroup of G. Okay, let's see some basic, we will look at a lot of examples in the next lecture, but in this lecture, let us get some basic properties out of the way. So first of all is, suppose we have a group G and we have a subgroup of G. Then the identity of H is an element of G, but it's a priori not clear that it is also the identity of G, but that is the point we are making, that it is actually the same. The identity of H and the identity of G are the same. Okay, so let's prove this. So fix some arbitrary element in H. Okay. Uh, and the identity of H is, well, I should have said that. So identity of H is denoted by that, and identity of G is denoted by that. So then by the fact that EH is the identity of H, we have EH times A equals A. Okay. And now here is what we do. So we multiply by A inverse on both sides, and this inverse is taken in G. So this A inverse is the inverse of A in G, not in H. We can also talk about the inverse of A in H because H is a subgroup and A is an element of H. But no, we are taking this inverse in G. So let me put that in emphasis. All right, so we have that. And now by associativity, this thing is EH EG equals EG. But now the fact that EG is the identity of G and EH is some element of G, the left side is just EH and the right side is EG. So we have shown the equality of the two identities. And that's very convenient. Okay, similarly, we have the result that suppose we have a subgroup of a group G and X is some arbitrary element in H, then the inverse of X as taken in H is same as the inverse of inverse of X as taken in G. Right, so in the previous lemma, we were sensitive to the distinction that a priori the inverse of an element in H can be different from the inverse of the same element in G. But now we are making the point that actually we do not need to be so sensitive. Okay, so let's give a quick proof of it. So what we have is X into X inverse, where this inverse is taken in H. So this notation is used to, here we have used this to, or let me put a subscript here. So this is the inverse of X in H. This is legitimate because H is a subgroup under the binary operation restricted from G. So what is this? This is by definition EH. That's how inverses are defined. But we have already shown that EH is actually equal to EG. So what we have is that X times the inverse of X in H is equal to EG. But now if you recall the comment that we made at the beginning of this lecture, this implies that X inverse H is actually X inverse G, meaning the inverse of X in G, because there is a unique element in G which makes this equation true. And one such element is the inverse of X in H, of course. And that's it. Therefore, the two inverses are the same. So it's a very simple point, but it has to be absorbed, and this will be used later without warning that these things we will just use without even mentioning. Okay. So now let us look at a criterion to decide when a given subset of a group is actually a subgroup. So we start with a group and we start with the subset of it. So then that subset is a subgroup of G if and only if these two conditions are satisfied. The first condition is just closure under multiplication. The second is closure under inverses. All right, so let's prove this. One direction we have more or less already done, so I will do the other direction. So assume 1 and 2 hold. So assume H is a subset such that 1 and 2 hold. We want to show that H is a subgroup. What do we want to do? We want to show that this binary operation makes H into a group. Okay, and of course, again, this is legitimate because of 1. Okay. So, so first of all, we will show that first claim is that the identity of G is in H. Here is the proof. So I should have said that H is a non-empty set. That those are some silly things that we have to take care of. So H is a non-empty set. Fine. So pick some arbitrary element A in H. And now by 2, A inverse is also in H. And now by 1, A inverse is also in H. H is closed under multiplication. So this implies EG is in H. EG is the identity of G. So we have that. And since EG is the identity of G, it clearly serves as the identity of H. So associativity I did not check, sorry for that, but it follows from the associativity of the binary operation in G. So associativity I leave as an exercise. There is nothing to do there really. And we just showed identity. EG serves as an identity of H, and inverses. That's already built into 2, follows from 2. So H is a subgroup. I was a little bit sketchy in this argument, but I'm sure you can figure this out with this much hint. And the reverse direction is an exercise. What is the reverse direction? Here you start with the assumption that H is a subgroup of G and show these two things. So reverse direction is an exercise. All right, so next lecture we will look at a lot of examples of subgroups. And with this, I end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.